Alright, so let's go through the 2008 Try Yourself 1 satellite question. So if this satellite of mass M orbiting a planet of mass big M, which is I assume is Earth lah, no, radius R. So the radius of the orbit is about R, and of course the satellite and the planet may be considered to be point masses. Derive an expression right in terms of M, and R for the KE of the satellite and explain your working. Okay, so for the derivation of your working, right? Okay, so first thing you always start off with this sentence. So for example, the gravitational force of planet provides the centripetal force. For satellite to undergo circular motion. Okay, so every time you are asked to show something, always start off with an English sentence lah. Okay, so with this, right, of course we can actually write down the equation. So for example, I want to express the KE. KE normally is expressed in terms of half mv square, right? So of course now I want to express in terms of the gmm over r. So now is gmm over r square is equal to mv square over r. So that's this one is the G force, this one is the centripetal force, right? So you just need to multiply left and right hand side by R. So this will give you Gm m over R equal to mv square. Because you just multiply by R. Then this part is also multiplied by R. So the so-called R at the denominator is gone. Okay, with this, right, you can notice one thing is that my mv square looks very similar to half mv square. So what you need to do is just to multiply by half on the left and right hand side. So what I want, okay, so I just write Gm m over 2R is equal to half mv square. So in this case, you have shown already. So this one just multiply by half. This one you times half. Okay, so that is the very first part. Okay, for part 2, show that the satellite in orbit, right, the ratio is equal to -2. So what I want to do is actually to use the GP of the satellite divide by the K of the satellite. Okay, how do I actually do this? Very simple. For GP of the satellite, is not MGH, is negative GM over R. Then after that, the KE is what we derived earlier, right? So it's half, GM over 2R. So what you need to do is use this divide by this. You should be able to get -2, right? Okay, so next will be, I go to this part B. Okay, we are given the energy radius diagram. So this one is the GPE. GP is actually plotted for us, right? So this will be the GPE. So next part, on figure 3.1, we are asked to draw the variation of the orbital radius with the kinetic energy of the satellite. Your line should extend from 1.5 to 4 rp. Okay, so always remember there's always a reason why they ask us to calculate the ratio beforehand. So for example, right, if you look at 1.5, 1.5 is around here. So this 1.5, right? My GPE is roughly about -6.7 like that. -6.7, right? So since I know the ratio is about 2 times, means that my KE is about 3.3 like that. About 3.3, correct? So I just need to plot. So this is the first plot. Then second plot, I put at 2R, right? Okay, 2R, my GPE is about -5. -5 you divide by -2 is about 2.5. So you just plot 2.5 right here. Then so and so forth, right? Okay, I plot one last one, then after I just put them together. Okay, so the next will be -4, which is at here. 2.5 rp, right? So this is -4, means that you divide by -2, so this will give you 2. So after you plot all the points, right, you just need to connect the dots. So when you connect, you just make sure it's a smooth curve like that. That's it. So this will be the kinetic energy of the satellite, right? Okay, so this easy 2 marks. Okay, so the last part, 2. The mass of the satellite is given as such. So the radius of the orbit is now changed from 4R to 2R. So you can see that the radius actually decreases, meaning that my speed must increase. Because remember, right, as your radius decrease, your gravitational force acting on your satellite will be greater. So you need a greater speed in order to so-called escape the g-force of the earth. Okay, so using figure 3.1 to determine what is the change in the orbital speed of the satellite. Okay, so first, okay, imagine that we are at 4rp. At 4r, so at 4r, what is our GPE? I mean, what is our Ke? So kinetic energy, right, is equal to, let's see, okay, 4r is roughly about 2 point, okay, so it's about negative 2.5 divided by negative, okay, about 1.25 like that. So it's about 1.25 multiplied by, let's see the, okay, so there's a, okay, so you look at the y-axis, 10 to the power of 9, so just put 10 to the power of 9 first. 10 to the power of 9 joule. So I want to determine what is the speed at 4r. So half m v square, right, is equal to 1.25 times 10 9. So since I know, oh, my m is about 1600, right, so I just need to calculate. So about 800 v square equal to 1.25 times 10 9. So my v square is equal to, let's see, 1.25 times 10 to the power of 9 divided by 800. So it's about 1562 500. V is equal to square root of that. Okay, so it's about 1250 meter per second. So that's the at 4r. Okay, at 2r, so what is my Ke? Ke will be equal to, let's see, okay, 2r is right here. Okay, 2r is okay, about roughly 2.5 like that, 2.5. Okay, 2.5 times 10 9 joule. So half m v square, 2.5 10 9. So 800 again, v square 2.5 times 10 9. So v square equal to 2.5 times 10 to the power of 9 divided by 800. So it's about 3125,000. So v is equal to 3125,000. So it's about 1767.7, so and so forth, right? Okay, just round off to 1770 meter per second. Yeah, so at 2r, right, my speed is 1770 meter per second. So I simply, because they say they want to change, so this one is not an answer yet. So what you need to do is use this thing minus away this thing. So the change in your speed, delta v, is equal to 176 1767 minus away 1250. So this will give you about, okay, I round off to 3SF, 518 meter per second. So that is how we actually do this question. Actually quite simple. So as long as you know how to plot, how to calculate, right? So this question actually is quite manageable.